Good. So, so my cameraman tells me that the last few minutes of the previous lecture were not taped, so I'll just repeat what I said, which in general relativity, the coordinates x and t are exactly arbitrary parameters around the on the motions, and the actual variables are not these, are in the metric itself, the value of the clock being a function, some of this function of the metric given by this function here, and of course you have many clocks labeled by arbitrary world lines. So let's make this concrete and go to the Hamilton-Jacobi formulation of general relativity. This was worked out in 1962 by Perez, which is not Alessandro Perez, whose office is nearby, because in 62 Alejandro Perez was not doing much physics yet. So Hamilton-Jacobi general relativity. Perez, 1962, and it was worked out by him on the basis of the work of Arnovit and Misner that was just before, whose work was based on the work by Dirac essentially, and also Peter Bergman. Dirac is the first who understood all this which I'm telling you, and in fact he's the first who understood that Hamiltonian mechanic has to be generalized because because of general relativity. He has a paper whose title is Generalized Hamiltonian Mechanics, whose content is exactly what I told you in a language that has since evolved. A lot of people have worked on this general formalism, and there are a variety of variants of it, but the structure I've given you is the one that seems simplest to me. Uno, due. Problems? How it works? Uno, due, tre, uno, due, tre. Okay, let me go ahead. So we need two things. We need a extended configuration space, and then the general relativistic Hamiltonian or the Hamilton-Jacobi equation. So let me write both. The extended configuration space can be taken to be the space, a space of three-dimensional Euclidean Riemannian matrix. I use the notation QAB of X, where A and B here are 1, 2, 3. Or sometimes I would just write QAB. So this is a field, of course, in 3 dimension, and a geometrical interpretation, of course, is a 3-dimensional metric, it's a 3-dimensional shape. I'll be a little bit more precise in a moment. So out of this, the extended phase space is gamma extended can be coordinatized by a metric, and its conjugate momentum, which is a field in 3 dimensions with 2 indices, each taking value of 1 to 3, symmetric, like this is symmetric. And the Hamilton-Jacobi equation is the following. In fact, there are two, but the second is immediate. Is let me put the Newton constant, g square QAB QCD minus 1/2 QAC QBD. The functional derivative of a functional on the extended configuration space, so a functional of these objects here. I also use the notation QAB simply without putting the x explicitly. Functional derivative with respect to QAC of x times the functional derivative with respect to QBD of x minus what is it? Determinant of g, which is a function of x, are the Ricci scalar of QAB, which is also a function of x. This is the three-dimensional Ricci scalar of this three metric here. So this is the Hamilton-Jacobi equation written by Perex in 62. It should be supplemented by another equation for this object here, which can be written in the following form. Just S of QEB is the same of has the same value on QAB tilde if QAB tilde and QAB are related by diffeomorphism. And you know how a metric transform under diffeomorphism, right? Q tilde AB of x tilde is dx over dx tilde A, dx over dx tilde B, CD, QCD of x tilde. The standard transformation of diffeomorphism. So this equation is simply saying that S, the Hamilton-Jacobi function, is not really a function of this field here, but is a function of the equivalence class of this field under diffeomorphism. So it is the same whatever you write the coordinates. It's actually a function of the geometry of this surface. Okay? Now, notice that this is, giving this is equivalent to give the Einstein equations. So if you write this is without matter, but you can add a matter term. I'm not going into that. I'm just doing classical. Yes?
Where is the equal sign in the first equal 0?
Thank you. This is the Hamilton-Jacobi equation. You're right. I was writing the Hamilton-Jacobi equation. So this equals 0. Sorry. That's right. So that's the Hamilton-Jacobi equation. This is equal to that. Notice that there's no t here. You don't need t. The t coordinate is the general covariant coordinate. T is not needed to do calculation of general relativity. It's an auxiliary thing to simplify the calculations. The information is not in t.
This is three-dimensional. Is it like?
I'm gonna. No. This is four-dimensional GR. This is four-dimensional GR. And I'll say in a minute how you do it. Now, of course, this is not an easy equation to solve, right? If we knew the general solution of the, if you know a general enough solution of this equation, it would be equivalent to knowing the solution of Einstein equations, which of course we don't. So let me tell you how to think about that. By thinking about the Hamilton function, which is a solution of that, a special class of solution of that, of GR. And so I become a little bit more precise here. And the Hamilton function, remember, is going to be a function of some initial metric. Let me write x just to be clear, and a final metric. Such that it is a solution of this equation in both set of variables, and here's a way to think about that. Think in space-time that you have a space-like three-dimensional surface, this one, and a space-like three-dimensional surface, this one, that join at some two-dimensional boundary. So you have something like that, the past, the future, okay? And you're interested in how space-time evolve from one to the other. Okay? So the initial metric sits here, the final metric sits here, and you're into the solution. You have this Hamilton function that solves this in both sets of variables, and you can you can compute this as a function, or determine what are the conditions of this as a function of the initial position and momentum, of course, because to evolve you need initial position and momentum. How you do it? Well, in the standard way. You take the functional derivative of ds over dqa initial. You put it equal to qab initial of x. When you compute this derivative here, you have an explicit function of functional of the initial metric, and let me just write that, and final metric. So by this, this is fixed. You have this equation here. So given the initial position, given the initial momentum of the initial metric, you have a condition of the final metric. Right? You get a single final metric? No, of course, because a lot of final metrics is going to solve that. This one, and this one, and this one. Now, what is this? Well, of course, you know what it is. It is the action, square root of gr, computed on the four-dimensional metric g mu nu, which solves the Einstein equation and is bounded by this initial three-dimensional metric and this initial four-dimensional metric. So if you know the Einstein equation, if you could solve everything, you could easily compute the Hamilton-Jacobi function. Given an initial metric and a final one, you compute whatever is in between. You integrate this thing here on this region R, and you have that. Vice versa, if you had that, you could compute the evolution of Q final given Q initial and P initial. Notice that everything is local in space-time. We don't need asymptotic, we don't need to go to infinity. General relativity is a local theory. It tells what happened in some region. If you have some metric here, and it's conjugate momentum here, and you can evolve, and everything is local in space-time. If you do this game explicitly, the momentum has a geometrical interpretation and is related to the time derivative of the metric, and is related to the extrinsic curvature of the metric. The time derivative is related to the extrinsic curvature. It's pretty obvious to think extrinsic curvature is how the surface is curved in four-dimensional geometry. So of course, if it's curved that way, you move it parallel to itself, the metric changes. If it's zero curved, it doesn't change. So it's clearly the Q dot time derivative of the metric is related to the extrinsic curvature. There are differential geometry formulas for that, which I'm not writing down because I don't need them. Now, formally, so keep this in mind. And formally, meaning with some ill-defined in mathematics. In the quantum theory, the coordinate, namely the 3 metric and its conjugate momentum, should go to non-commuting operators, an algebra, right? And so up to ill-defined mathematics, and the entire game of the next couple of lecture will be to replace the ill-defined mathematics with well-defined mathematics. So to do this for real, so let's first do it formally, and then let's do it for real. Let's take in this non-commuting set a maximal commuting set. Let's say that is this one for simplicity. So we expect to have something like eigenstate of a 3 geometry. Let me use this notation here without the x. So this is a 3 geometry. Of course, not a metric, but a 3 geometry because of this equation here. And what we want to compute is amplitude, quantum amplitude, of going from an initial 3 geometry to a final 3 geometry. That's what we want to compute. Given an amplitude of some 3 geometry here, and maybe some matter here, we want to know the probabilities of getting to a final 3 geometry here, probably with matter here. That's what we want to compute. Now formally, this is the functional integral on 4 geometries of e to the I h bar, the Einstein-Lie reduction, the integral of square root of gr. Formally. Which, again, formally is going to be dominated by the classical solutions. So, assuming that there is a single classical solution going from this geometry to this geometry, this is going to be approximated by e to the I h bar, this Hamilton-Jacobi function, exactly the objects I have defined here, with the initial and final 3 geometries, right? And this, I expect this object here to satisfy the quantum version of this equation here, and this one to be the iconal approximation of the quantum equation satisfying this one. So let me say what I mean here. Let's go one moment back to the previous case. Remember that the infinite dimension we had C of QA PA equals 0. We had the Hamilton-Jacobi function, the Hamilton-Jacobi equation ds over dqa equals 0. And we had the solution, which are QA initial, QA final. And the transition amplitude, the quantum transition amplitude, QA initial, QA final, which are given as a functional integral on the trajectories dq of tau of e to the I h bar s of q of tau on the with boundary conditions given by this. Now, these transition amplitudes satisfy the equation C of QA I minus IH bar D over dQA W QA initial QA final equals 0. Which can formally derive directly from this in both set of variables, so in both in the initial and the final variable, and this is what is generically called the Wheeler-DeWitt equation. In the special case where the constraint have the form pt minus h of pi qi, this Wheeler-DeWitt equation becomes, this term here is I h bar d over dt minus h of qi d I h bar d over d qi psi w equals 0, which is a Schrodinger equation. Okay? So what is a Schrodinger equation? Is a special case of the Wheeler-DeWitt equation, which is an equation satisfied by the transition amplitudes in the general covariant formalism when the relativistic Hamiltonian has the Newtonian non-relativistic form. Okay? So the Schrodinger equation is just valid for quantum mechanics when there is a Newtonian time, but we know what is its generalization, it's just this equation here. That's simple. So when people say, does quantum mechanics need to be changed to do quantum gravity? The answer is yes, a little bit. It has to be generalized in order to keep into account the fact that there is no Newtonian time. The time variable is mixed with the other one. So the quantum algebra of operator that you need is the general relativistic one, is the one with QAPA. And the dynamical equation that the amplitude satisfy is the Wheeler-DeWitt equation, the general form of the Wheeler-DeWitt equation, which reduces to the Schrodinger equation in the special case in which you can choose one particular variable, and in that particular variable the Hamiltonian has this form here. Okay? So the structure of quantum mechanics remains the same in the non-Newtonian case, but with a little bit of tweaking and a more general form of the Schrodinger equation, which is this one. So when people panic that there is no Schrodinger equation in quantum mechanics because there's no time general relativity, there's no reason to panic because this generalizes easily to this one. Okay? This is in general for all theory without Newtonian time. When you go to quantum gravity, formally, this transition amplitude satisfies this equation where the constraint, the Hamiltonian constraint of the relativistic Hamiltonian is this one. So these transition amplitudes satisfy this equation where, however, here you do not have ds of dq, but you just have functional derivatives in this manner here, and that's the equation that Wheeler-DeWitt wrote in 1963. In fact, immediately after Paris wrote this Hamilton-Jacobi formulation of GR. Notice that all the funny part about time is in the classical theory, it's not in the step to the quantum case. The step to the quantum case is immediate once you understand how is peculiarly treated time in general relativity. So these transition amplitudes satisfy the equation. Let me write it a little bit more sketchy. Let me write all this as G, A, B, C, D. So these transition amplitudes satisfy, let me call them, let me call this W, Q, F, A, B, Q in A, B. And they satisfy G, A, B, C, D, D over dq AB, D over dq CD, minus GR, W, QAB, QCD equals 0, in, out, in fact, both in the in variable and the out variable, so I don't write this. And that's the Wheeler-DeWitt equation, 1964 or something like that.
Sometimes people in quantum mechanics discuss if there exists or not an operator for time. It seems that with this formulation of quantum mechanics, it's pretty obvious that time is on the same level as the x, and so there should exist also a time operator just as there.
Yeah, of course. Yeah, there is an operator for time. Of course, then the transition amplitude don't give the evolution of the time variable with respect to something else. Give the relative evolution of things, but a priori there is nothing that forbids this operator to exist. In fact, one can use this general language to do a free particle and show that everything is well defined and everything functions. The Hilbert space of the theory should not be identified with a Hilbert space on which the operators QA and PA act. So this act on some extended Hilbert space. The Hilbert space of the theory is then the space of the solutions of this equation here. The usual Hilbert space is smaller because there's this equation here.
However, it seems that in the axioms, the Born rule gives strong importance for the interpretation of probability and time. So, what becomes the Born rule?
Oh, very good, very good, very good. Remember, that's why I did all the discussion at the beginning. Time means different things. Let's not confuse the different meaning of time. So let's use the Born rule here. Let's talk a la Copenhagen. We could have a different language, but let's talk a la Copenhagen with probabilities and measurement. You measure something here, okay, and out of your measurement you detect that the state is this one. Then you have a probability distribution from the various state this one, the probability distribution given by the model square of these amplitudes here. If you measure something here, you're going to project on this one of the eigenstates of what you measure. If you want to think in terms of Copenhagen quantum mechanics. So you see that you have a before, a later, an interaction, and time in this sense is there all the time. But you don't need a t variable for doing that. What you need is initial variable and final variables. So there is an order. What is not is a specific one of the variables here chosen as the one needed for tracking time. Remember Aristotle's definition of time. It's a number of change. If you choose one of these variables, you can use it for tracking time, but you can choose any one. Which how we're doing with time, which takes me, I want to conclude this, but takes me for no, I can since you ask this, let me open a parenthesis on this, because this is a good way of, a good moment of putting it before going back to that story. In Copenhagen quantum mechanics, there is a system, and there is something called the observer, which interacts with the system, and it does measurement. Of course, this is a silly language, right? Because what nature knows about measurement, nature is the same. Doesn't know whether there's a physicist making a measurement or a stone falling or something being pushed by something else. So measurement is just an interaction. So what quantum mechanics says is it talks about interaction between systems, and with variables of this system here, which take values when they interact with something else, and quantum mechanics gives probability distribution of these values. Quantum mechanics, in fact, does two things. It gives the possible values that variable can take, and this is the spectra of the Q's and the P's, and it gives probabilities of values as a function of what? As a function of values measured before, so as a function of previous values that were taken by the variables. Now, this can be used in quantum gravity in this scheme. You have values here, and given some value taken here, you give a probability distribution of the value there. Which is, you think for a moment, is something spectacularly nice. Because quantum mechanics is a relation between systems which interact. General relativity is a relation between space-time regions which are contiguous to one another. So this boundary here, which is, of course, is artificial, like this boundary here is artificial, but is needed to do quantum mechanics, is a boundary between how one part of the world affects another part of the world. But in quantum mechanics, it's about system interacting. In quantum gravity, it's about space-time region interacting with one another. And of course, the theory is smart, and it doesn't depend where you put the boundary. If you put the boundary here, this is Wigner-Friend's argument. You can put the boundary between one system and the other wherever you want, to some extent. You can move it out as you want, and the final probability are the same. So there is nothing physical about the boundary, but there is something physical about how the system affects its outside. And this in turn will affect it outside in a manner which is determined by the quantum mechanics of this one, and so on and so forth. And in quantum gravity, the beautiful thing that happens is that a system is identified with a space-time region. Okay, and the interaction, it's where the space-time are contiguous. It's contiguity. Which, if you think about, is the greatest discovery of 20th century physics, is locality. To interact, you have to be next to one. You have to be near, contiguous. It's locality. And vice versa, what else is to be close, if not the fact that you can interact? So the picture here is that you can do quantum gravity or finite region of space-time, and the way they interact with one another is a quantum mechanical way in which systems interact with one another. Physics is local in this sense. You don't need asymptotic, you don't need infinity, And the standard language of quantum theory and the standard language of relativity talks to one another very well. To do that, what you need is to compute these quantities here and these operators here. And what we have already done is to study these operators. What we still have to do is to compute these quantities here. So let me sketch what we have to do next. We have to take away this formally and write these quantities here explicitly, perhaps in perturbation theory, perhaps order by order in some expansion. I mean, we're not going to solve the theory explicitly, but say how we have to compute them. Now, what are the conditions of this quantity and what is formally and what we have to make precise? Well, the condition of this quantity is that in the classical limit they should give GR. Right? We should define a quantum theory such that in the classical limit they should give GR. Which means that in the classical limit, when h bar is small, this should be, to first order, I h bar s of QAB in QAB out. Well, this is the Hamilton-Jacobi Equation of general relativity. It's a perfectly well-defined object. Right? That's what we want. So can we define quantities which are proper quantum transition amplitudes that behave in this way in the h bar going to zero limit? That's our task, and that's what I will do tomorrow. Now, to do that, of course, formally, here they are. We just do the functional integral on the 4 geometry, where on a 4 geometry bounded by regions with given initial and final symmetrics. But these are formal for various regions, so why are they formal? So why is this all ill-defined? Well, first of all, nobody knows how to give meaning to this integral just written out of that. This measure dg is ill-defined. So we have to do something to make it more precise. Second, the Wheeler-DeWitt equation that I wrote down, if you remember, there was a functional derivative QAB of x, QCD of x, and this product of functional derivatives is defined mathematically. This is a distribution. This can be defined cleanly as a distribution. It's a product of distribution, which is opens all the standard problem of quantum field theory. So functional derivatives ill-defined. So we have to circumvent this in some way. And third, we have to find a way to define these operators, but in fact we did, right? Because this operator should define the quantum geometry of a 3-dimensional region of this and this. But that's what we did in all the kinematical part. That's the Hilbert space and the operators that we wrote down. But remember, this is actually general. Remember that this thing here are not geometries. These are labels of the eigenstate that diagonalize a maximally commuting set of operators. Right? In general. I mean, the transition amplitude of quantum mechanics are not transition amplitude between classical value and classical value. They are so only when the relevant observable have continuous spectrum. In general, the transition amplitudes, I mean, people doing atomic physics do transition amplitudes between one energy level to another energy level. So give transition amplitude from NLM to N prime, L prime, M prime. Not classical. So these are, in the non-formal theory, these have to be labels, these have to be quantum numbers. Quantum numbers of the operators, of those operators, of the Q operators. So what we actually need is not really W of QA initial, QA final, so QAB initial, QAB final. So not really from a classical 3 geometry to a classical 3 geometry, but from an eigenstate of the geometry here and an eigenstate of the geometry here. Because, to go back to the Copenhagen interpretation, if I measure the geometry here, I get only certain values and not others. So we want quantum numbers, and we know the quantum numbers. Okay? This is what happened in the first part of the course. This is going to be a function of a spin network. JLVN gamma JLVN in and out, in and out, in and out, in out, out. So we want something that, given an initial spin network and a final spin network, gives a complex number such that in the h bar going to 0 limit, this complex number is e to the I h bar, the Hamilton function of the 4-dimensional geometry determined by the geometry approximated by the quantum discrete geometry here and the quantum discrete geometry there. Okay? So this should be such that for small h bar goes to I over h bar s of some metric determined by the spin formula. Just write it formally. But the spin network, sorry. And that's what I'm going to build. I'm going to build this quantity explicitly, order by order in some truncation. I'm going to give it to you with some motivations, give a formula. And this quantity will be finite. So no ultraviolet divergences. And would have the property, a suitable property that is related to the action of classical GR in this way, with some caveats we will discuss. Right? So you have the scheme of what we want, how to do quantum gravity, what are the ingredients. The game is just to do it and write it. And this was the explicit formula of that was found a few years ago, in fact, by a number of groups, and was collaborations here in Marseille played a key role. Polish people played a key role in England, in Canada. There were people playing key role, and we have an explicit expression for that. So I'm going to write it down in the next lecture. It will be a little bit of preliminary mathematical work, but you will see how it is done. Questions? No questions? Stop here.